quick recap. So far, you have learned to simplify a radical expression. Just a basic, if I say square root of 50, can you recognize there's still perfect squares in there and square root what you can? Simplifying radicals. You've also learned how to simplify radical expressions that involve addition. That's where you have to get the radicand the same so that you can put it together. Now we're going to look at a different operation with radicals. So get out page 10. Make sure you're looking at page 10. You got a pen, pencil in hand. For the top three, I'm actually about to show you the answers to those three, and then we're going to go back and try to figure out why those answers are what they are. So looking at page 10, here we go. All right, so on part A right here, I told you the answer to this, and I also showed you right here in the calculator, just in case you don't believe me, the square root of 2 times the square root of 2 equals 2. What? Why? I don't know. Let's look at this one. Square root of 8 times the square root of 8 equals 8. Huh, interesting. And look at this one. The square root of 2 times the square root of 8 equals 4. Why? Why is that happening? Well, in order to tell why that is happening and where those answers are coming from, let's put one example up on the top for ourselves here. One thing that we know from when we were simplifying, for example, if I started you with square root of 50, we would factor that and we'd say, okay, this is hopefully a pretty common one that you're starting to recognize right away. 50 is really 25 times 2. And then actually what we did at that point is we separated them so that they were each a part of their own radical expression. We did this process, we'd factor it, and then we went, oh, I can break it apart and do the square root of each of them separately. And the reason we did that is so that we could then square root the perfect square part and leave the other part inside the radical. Well, this actually is showing me that I can go the other way. Instead of factoring it and separating it out, look, this is already factored and separated out. So instead of factoring and working out this way, what if I work back this way and realize that if I have square root of 25 times square root of 2, I can just make that the square root of 25 times 2 and put it all under its own radical. That is precisely what is happening here. Instead of square root of 2 times square root of 2, I'm going to put it all under the same radical, square root of 2 times 2. Well, let's actually do that multiplication. Hey, that's square root of 4. And oh my goodness, what is the square root of 4? It is, of course, 2. That's what's going on there. Watch what happens on this one. Okay, if I just put these back together under the same radical, 8 times 8, and actually do that multiplication, square root of 64, what is the square root of 64? It is, of course, 8. Why? Because 64 is a perfect square. So that's what's really happening there. Well, what about this one? What about when you change things? Can you still do that? Watch. Put them back together underneath the radical, 2 times 8. Do that multiplication. 2 times 8 is 16. And what do you know? Square root of 16 is 4. As you've probably guessed, though, it doesn't always come out to a nice perfect square. But what this shows me up here is that I can, in fact, instead of separating it out to simplify, I can also go the other way. I can multiply those radicands and put them back together under a radical. And sometimes that makes it easier to simplify things. So let's give ourselves right here in this box. Let's show ourselves in general terms with variables, what's actually going on when we multiply a radical. Give ourselves a mathematical rule here. So none of these had a coefficient, but I'm going to tell you right now, you often will. If you have a radical expression that looks like this, a square root of b, that's how we say that out loud. A square root of b. And we know, even though they don't write it here, we know that that automatically means multiplication. It's a coefficient. If you multiply that by another radical expression, and this looks kind of funny, it looks like the a is higher than the b. It's not. Those are mathematically written on the same level. Okay, it's not like an exponent or anything weird like that. It looks like that. If I have one radical expression, a square root of b, times another radical expression, I'm going to call it c square root of, and since I'm writing them really big, I'm going to put this little part in because that's actually part of the symbol. I just never write it. A square root of B times C square root of D. I'm using all different letters for those because they can be all different letters, okay? Here's how it works. We simply multiply all the matching pieces. These are called coefficients. We've said that word a few times. These are called coefficients. Say that word to yourself. What are those called? Coefficients. These are called radicands. That's a fun word. What are those called? Radicands. So to multiply radical expressions, you simply multiply the coefficients. We're going to do A times C, multiply the coefficients, and multiply the radicands. And because they're radicands, when you multiply them, just like up here, they all just come together under one radical. So I'm going to put my radical symbol, my square root, and multiply the radicands. That's it. Oh, except for, of course, that's not really it. What we always have to do, the whole point of this is still called simplifying radical expressions. So, of course, at this point, I'm going to put a couple stars here. Oh, there's an announcement.
They are about to turn off the water to the building.
Hear that? Oh.
FYI.
Okay, so luckily you guys are already gone. Then you simplify. So to multiply radical expressions, you multiply the radicands. I just pointed to the coefficients and said radicands. Multiply the coefficients, multiply the radicands, and then simplify whatever you can in there. We're going to practice it in just a second, but first I just want to give us a couple of clarifying things, because this is how sometimes we learn something new in mathematics about radicals and we're like, oh my gosh, it's something else brand new, always brand new things. This is actually how everything kind of works in mathematics. It just looks a little different based on the type of numbers. Let's give ourselves some notes over here so that you see what I'm talking about. To make sure you recall this, okay, in mathematics, everything that is addition, adding things have to be the same size, and they keep that size. When you add centimeters to centimeters, they're still centimeters. When you add fourths to fourths, they're still fourths. That's true with radicals as well. So let's give ourselves just some general ideas here. Like if I have square root of 2 plus square root of 2, that is now just two of them. Remember, there's ones in front here. So 1 square root of 2 plus 1 square root of 2 is just 2 square root of 2. That's what it is now, okay? However, if I multiply, it's going to look very similar, but it's going to have a very different answer. If I do square root of 2 times square root of 2, when you multiply, you actually change the size of things. Square root of 2 times square root of 2 is square root of 4, which comes out to 2. So the operation addition and multiplication in all things mathematics, so much of mathematics comes down to just how addition works versus how multiplication works. So make sure you have this straight in your brain. That square root of 2 plus square root of 2 is 2 of them, but they're still square roots of 2. Square root of 2 times square root of 2 is 4. Entirely different thing. So when you're adding, don't change the radicand. When you're multiplying, you will change the radicand. So let's put that also just in general terms with variables. What this means is if I have square root of x plus square root of x, that's just going to give me 2 of them, 2 square root of x. Whereas if I do square root of x times square root of x, watch this. This is going to give me square root of x squared, which is where that inverse operation comes in, and the squaring and the square rooting cancel each other, and you just end up with x. So it's just a difference in how addition works versus how multiplication works. Everything in mathematics, it's true for fractions. For fractions, if you're adding, you get a common denominator and you keep that size. A fourth plus a fourth is a fourth. If you're multiplying, though, a fourth times a fourth is no longer a fourth, it's a 16th. So, and you can do things like a fourth times a half, which is an eighth. So when you're adding, things have to be the same size. When you're multiplying, they don't have to be the same size because it's going to change sizes anyway. And that'll kind of become a common theme as we work through lots of different kinds of numbers this year. Okay, so let's actually put that into practice and let's try some multiplying with radicals. Here we go. All I have to do to start is put these back together as a product under the radical. First step, just multiply those radicands. Put them back together under the radical. Now I am going to actually multiply those. 12 times 6 is 72. And then you simplify. That's what we've been practicing a lot the last couple of days. That's what we're going to keep practicing more today, simplifying. Okay, so this is where you can choose. I'm going to break this down and I'm going to do the factor tree, or hopefully you can even just flip your paper over and go, hey, these are the numbers that are allowed to be left in the radicand. I'm going to start dividing by those until I get one of those. Remember, I am dividing by these until I get one of these. All right, so 72 divided by 2. That's the very first one on my list of things that are allowed to stay inside the radical. 72 divided by 2 is 36. Is 36 a perfect square? Yes, it is. I promise this really is a super fast method if you start dividing by what is allowed to stay inside. So 36 times 2. So I am now, to simplify, I'm now going to break it back apart, but I'm going to break it apart into factors that help me simplify it. 12 and 6 don't help me simplify it because neither of them are perfect squares. So I multiplied them. I got myself here to 72, and now I'm going to split it back up. You ready? I'm going to change colors just for the fun of it. I'm going to split it back up into, instead of 12 and 6, I'm going to use 36 and 2. If you would prefer to use a factor tree and for every pair take out 1, that's great too. Go ahead and do that. This now is the part I can square root, and my simplified answer is 6 square root of 2. And just in case you forgot, if you're looking at this and you're like, wow, we have all these different ways to write this. Are they really the same? You can always test it out in your calculator. The answer I want here is not a decimal. Do not type decimals in any of your Canvas practice. You will get them all wrong, because I'm not looking for decimal approximations. I'm looking for simplified radicals. But if I type in my calculator right now, square root of 12, I don't need all those parentheses, square root of 12, you have to close that parenthesis. Otherwise, it'll think this next part is still inside that square root. So I'm going to go square root of 12 times square root of 6. And I'm just getting this decimal approximation to verify that what I have here has worked. So I got this 8.4852. I'm going to type this in, 6 square root of 2. Clear. I did 22 and that was not looking right. There it is, 8.4852. And guess what? I could even type this one in just to verify that everything I'm doing really, even though it looks different, it's all actually the same. But what we have here in blue is the official, and that video you watched before practicing on the Nearpod, it talked to you about just things that we do, customs that we follow in mathematics. It's customary to get yourself to the most simplified radical, and that is what we have there in blue. We don't have it there. We don't have it there in purple. We have it right there in blue. Okay, let's try this again. This time we have coefficients. This is a -1 and this is a -3. You multiply the coefficients, and please remember, if you've forgotten this since 7th grade, ask yourself, what is a negative times a negative? It is absolutely a positive, okay? A negative times a negative is a positive. So right here, -1 times -3 is 3. I multiplied the coefficients, that's this part, AC, A times C. I multiplied the coefficients and it's still a coefficient. Now I'm going to multiply the radicands, 10 times 10, and that will still be a radicand. I really hope right now that you don't go through and make a factor tree out of 100 or start dividing 100 by a whole bunch of things. I hope that you recognize the number 100 is right on this perfect squares list. Do you know what that means? That means this simply goes like this. There is no more radical because you square root it and everything gets square rooted. So you don't need the symbol anymore. You took that action of square root, so the symbol is gone. So 3 times 10, this whole thing comes all the way down to 30. And if you want to, you can pause this video and type all that in your calculator and you'll see it. but that is certainly simplified. We multiplied the coefficients, we multiplied the radicands. Let's try it again. Here we go. Number 3. I'm going to multiply the coefficients. There they are. Those are the coefficients. 3 times -2 is -6. When I multiply the coefficients, they are still coefficients. Now I'm going to multiply the radicands. That's big. 27 times 18 is 486. That's still in the radical. That might be kind of annoying to do a factor tree with. You could do it, start dividing by 2, go from there. You'd be able to do it. Instead, start dividing by things that are allowed to stay in the radical. I always start with 2. I have in my head 2, 3, 5, and 6. Those are the most common ones. 2, 3, 5, and 6. So I'm going to start 486 divided by 2. Remember when I type this in, I am trying to figure out a perfect square. I'm trying to see if I get to a perfect square. So ready? Here we go. Is 243 a perfect square? No, it's not. Okay, so let's try the next one that's allowed to stay in the radical, 3. See if we get a perfect square. Is 162 a perfect square? No, it's not. Okay, the next one that's allowed to stay inside the radical is 5. This is not going to be divisible by 5 because it doesn't end in 5, but I'll just prove it to you. That's not a perfect square. What's the next one? 6. 6 is also allowed to stay in the radical. Feel free to flip your paper over and look at that list if you need to. Let's see if we get a perfect square. Is 81 a perfect square? Yes, it is, because it's 9 times 9. So that's what I want right here. So now I'm going to split this up, and these are my factors right here. This was the original radicand, so I need 81 times 6. That's what I'm looking for here, 81 times 6. So don't forget you already have a coefficient. You already have -6 as a coefficient here. We are now breaking this back up into useful factors of 81 times 6. Now I get to square root just the perfect square part. The square root of 81 is 9 because it's the opposite of squaring. The 6 does not have a perfect square. It has to stay inside. My final step is clean this up here. -54 square root of 6. Multiplication. Okay, we're just going to do 2 more, and then we're actually going to, I'll show you what we're going to do on the last one. So number 4, here's what I see on number 4. This is a multiplication problem here, and then we have this subtraction attached to it. I'm not going to worry about that just yet. What I am going to do is multiply those radicands and put them all under the same radical. So I just have one factor to deal with. And then I'm going to copy this. Okay. Now this is a subtraction problem, which all of subtraction is really addition, so it's all the same stuff. So this is what we were working on a couple days ago and what we practiced yesterday. So now I need to simplify these. I can't combine them right now because the radicands are different. Now I'm switching my brain from multiplication back over to addition. So I am going to, let's see, 48 divided by 2 is 24. 24 is not a perfect square. 48 divided by 3 is 16. 16 times 3. 16 is a perfect square. -4. There's a couple common ones that start to come up a lot. Square root of 75. 75 will always break down to 25 and 3. You'll also, I hope you started to notice the last couple of days that when it's an addition or subtraction problem, you usually get a hint. You're usually going to be able to put them together, and so probably these, what's allowed to be left in the radical might end up as the same number. So I'm going to square root these perfect square parts. Ready? Square root of 16 is 4. The 3 stays inside. This coefficient is already there. Don't forget about it. But now I'm going to times it by a 5. Why? Because square root of 25 brings out a 5. The other 3 stays inside. Now I clean this up some more. 4 times 5 is 20. Now I remember my integer rules from 7th grade. 4 minus 20 is -16 square root of 3. This is the coefficient. This is the radicand. And on your Canvas quiz, that's how you type them in, right? You write all this down and figure it out, and then you type in your coefficient and your radicand. All right, one more example here. Number 5. Do you remember this thing right here? I'm going to write it over here. That is called the distributive property. And that is still multiplication. It's just multiplication twice. And that is precisely what we need right here. Okay, so I am going to remember, first of all, okay, those just have ones in front, but I'm going to multiply those radical expressions. And then I'm going to multiply those radical expressions. Square root of 5 times square root of 10 is square root of 50. Right? I just multiplied the radicands. Yes, there were coefficients, but they were both 1, so it stayed a 1. 1 times 1 is 1. Okay? Now right here, this coefficient of 1 is going to be multiplied by this coefficient of negative 2. 1 times negative 2 is negative 2. Now I multiply the radicands. Square root of 20. Okay? So, square root of 50 breaks down to 25 times 2, largest perfect square factor. This coefficient is already there. 20. Let's see. Things allowed to stay in the radical, 2, 3, 5, 6. I remember those first 4. 20 divided by 2 is 10. 10 is not a perfect square. 20 divided by 3 is not divisible by 3. 20 divided by 5 is 4. 4 is a perfect square. We don't often get 4 to be the largest one, but for 20 it is. It's just 4 times 5. Now, I am going to square root the parts that I can. Square root of 25 is 5. The 2 stays inside. This coefficient is already there. Square root of 4 is 2. The 5 stays inside. 5 square root of 2 minus 2 times 2 is 4 square root of 5. Huh. Can I do anything with that? I'm so used to things just like working out that I can do stuff with it. But if these radicands are different, I'm going to stop right there. Now, you are welcome to try number 6 if you want to. For the purposes of what you're practicing today, I don't think we really need this example. So I'm going to write this fun, fancy word right here. And when you take a picture of your notes and submit it to your math teacher, if yours says skip also, that's all good and fine because we all wrote that. All right, you are now going to get one more practice on simplifying radical expressions to try and help you understand and be ready for an assessment on this stuff. What do you need to know? You need to know how to simplify a radical. You need to know how to simplify radical expressions with addition or subtraction. And you need to know how to multiply them. And then finish simplifying. So, give your practice a try. Let me know if you have any questions. You guys got this.